have three types of intermolecular attraction. I don't remember, yesterday, did we copy any of this down? Did I say, hey, at least write it down? I thought I did, but I didn't. Okay, then. Molecular compounds they're attracted to one another to some extent, some better than others. All molecular compounds have some attraction for one another, even hydrogen molecules, H2. There's a little tiny bit of attraction. There's not very much. Hydrogen is nearly an ideal gas because there's such little attraction between the molecules, but there is some. And the types of attractions that a molecule has determines what kind of properties it's going to have. The intermolecular attractions determine whether something is going to be a solid, liquid, or gas. It determines how high its boiling point is going to be and how low its freezing point is going to be. Intermolecular attractions determine what the vapor pressure of something is going to be. And so there's a lot of properties that are determined by this. The weakest are the London dispersion forces. They're weak, but every molecule has some amount of London dispersion forces. So everything is going to fall under this type of intermolecular attraction. It's just how much does one thing have over another. Here's two atoms. That represents either two atoms or two molecules. And they're coming toward each other. They're moving, of course. Molecules are always moving. And so these are coming toward each other. And have you ever seen a slow motion video of a tennis ball being hit by the racket or a baseball being hit by the bat? It's pretty fascinating, isn't it, how much deformity there is? Especially a tennis ball, man. The thing flattens out if somebody strong hits it. Now, these molecules that run into each other, they kind of do the same thing. They kind of deform. And can you imagine the moment after these two collide with one another? You're going to have something like this, where they start with, of course, the nucleus right in the middle, and this nucleus right in the middle. They're going to hit each other, and then there's a little bit of deformity that goes on, where the nucleus is temporarily not in the center of the atom. It's like this atom is going over here, and you kind of get this waviness of the electrons once the collision occurs. That is the kind of thing that I'm talking about with London dispersion forces, because particles are always in motion. Even in a solid, they're always in motion. And so because the electron cloud can kind of do this kind of thing, you'll sense that temporarily, just like the baseball when the bat is hitting it is temporarily deformed, temporarily we're going to have a side of the molecular atom that's electron rich, and a side of the molecular atom that's kind of proton rich because the nucleus has been pushed over to one side. So that means that for a moment, this thing is polar. Even if it wasn't polar before. For a moment, it's polar after that collision. And then the molecule kind of recovers and it goes on its way again, and then it's going to hit something else and do the same thing. So, and remember that in a sample of matter, you've got billions of particles. So at any given time, there's a whole bunch of them that have this polarity about them. That's what I'm describing up here. I'm using the term like temporary polarity. This is a temporary polarity. It doesn't last long, just for a moment. But then when this kind of recovers, it becomes neutral again with the nucleus in the middle. Then there's other atoms and molecules around it that are temporarily polar. So this causes molecules to kind of stick together. The bigger the molecules, the more electron clouds they have, the more that this electron waviness happens, and so the more the London forces are there. So that's why I have a list for you. What's the name of CH4?
Methane.
Good, methane. Second or third hour, they didn't have any ideas, like they never saw it. C2H6?
Oh. Oh, butane.
Now you're hurting me.
Butane.
No, thank you. You guys.
Wait, you said C2H6?
You gotta do some organic chemistry.
Oh, H6.
C2H6.
Sorry.
Okay, ethane. C3H8. Propane. C4H10.
Wait, oh, okay. Butane.
Butane, right? And then I have a line. C5H12, pentane, C6, hexane, and then down to C8, octane. I skipped C7, it's okay. I drew a line between those two. Are any of these polar molecules?
No,
How do you know?
because they're all non-polar.
There's no FONCl.
That's what I meant.
Right. I left it out. No polarity. So we only have, these molecules only have dispersion forces that they can depend on to attract them to one another. We'll see down here, the next one is dipole attraction, which means you have a polar molecule. Since these don't have any positive and negative sides, they're depending on their London dispersion forces to stick together. That's going to cause the molecules above the line to be gas at room temperature. They have very small molar masses. They're small molecules, they're non-polar, and they don't have much attraction for one another. As the molecules get bigger, starting with C5H12, these are all liquids. And that's because of the heavier the molecule, the more the dispersion forces are. Yeah. And so the heavier it is, the more the particles will stick together. Another example I could give you is the halogen family. Lena? Wait a minute. Weren't you the one pointing fingers at other people asking no questions?
No,
Just clarifying.
Yeah, it was. But C7 is included though in liquids.
Yes, it's included. It's saving time.
You're so sad. I need to stop.
What? What did I do?
Yes.
Vinny, for every question Lena asks, you get a question.
Oh, gee.
No.
For free.
Okay, I'll save it for later.
The halogen family. Fluorine, chlorine, bromine, iodine. All of them are diatomic molecules. All of these have molecules that make them up. Fluorine, chlorine. What do you know about their physical states?
Gaseous.
They're gas. What about bromine?
Liquid.
It's a liquid. What about iodine?
Gas,
It's
solid.
a great case in point that the heavier these nonpolar molecules get, the more their London dispersion force, and therefore they stick together more. And so you get to iodine, it's a brittle solid.
What do you mean the mass here? You mean like the heavier?
Molar masses, yeah. I mean, the molar mass goes along with the electron cloud. The heavier it is, the more electrons it's going to have. So the more electron waving around it does. Mohammed?
What if they're already polar?
Now, if they're already polar, you still can talk about the London dispersion forces. I'm just kind of making a control of only things that are non-polar, so we can just compare the London dispersion forces. But if they're polar, polar things tend to stick to one another and be liquids most of the time. There are some gases like ammonia that are polar, but they're gas. But most things are, even if they're small. Ammonia is just too small. It's got a molar mass of 17, and those particles are just too anxious to fly around. Yes?
Is there a point where they're just solids? Like gasoline?
Yeah, with the organics, I don't remember how many carbons it takes, but yeah, once you get to enough carbons, they're always solid. Yeah. Wax, I know, is C25 approximately. There's lots of different molecules for wax. But even before then, like I'm sure into the C mid-teens, they're all solids. Yeah. That's it.
And if you compare IQ with nitrogen, for example, because nitrogen is like polar.
No, nitrogen's not polar. It's not polar. And two,
And two, yeah.
it's not polar.
Well, you know, you said that, never mind.
Okay, so the next type of intermolecular attraction, I hate the name of this thing too. I think it should just be called dipole attraction. I don't see why they need to use the word twice.
Die.
I know, but I think just one word is enough. Dipole attractions, you got two ends, positive and negative. I guess. I like it. So dipole attractions will cause particles that are polar to be attracted to one another and come together and hang on to each other for them. Because opposite things attract one another. It was yesterday, I think it was a Chuth that realized nobody said anything. People were so polite, third and fourth hour, no, on second and third hour, because you didn't see this. And by fifth hour, Chuth said, hey, wait a minute, one of your molecules is wrong.
Yes, but.
You see it?
Yeah.
We've got a rogue molecule and they're a rebel. That one right there.
The rebel.
The positive's up against the next
How hard
one.
is it to draw?
Ah.
He called them.
Don't draw. If you're gonna draw that, don't draw it wrong like this guy did.
He texted me this the picture. He was like, "Them G dipoles." I was like, I don't know. Does he shout that a lot in class? Like them G something?
Them G.
Yeah.
With the G's.
Gangster.
Oh my god. Really?
I don't know. He just randomly texted me to them and he was like, "Oh, them G dipoles." That was my question
He
actually.
doesn't say that in my class.
You obviously are in AP, right?
Wait, that wasn't.
So dipole attractions tend to be a little bit stronger than London dispersion. I mean, when you get into heavy molecules, they're going to be solid anyway, and they're going to stick together just because of the London forces. But for smaller molecules, those that are polar. And another property that is very important to understand about intermolecular attractions is this is what determines whether some molecules will mix together with other molecules. Why do water and oil not mix together? Because water is a polar substance and oil is a non-polar substance. And polar things tend to want to interact with other charged polar things. They don't know what to do with something that doesn't have any charge, like a non-polar oil. So the non-polar things stick with one another and the polar things stick with one another. And they'll make two layers if you mix them together. Try this.
I'll use up my
Yeah.
question.
Go ahead.
What about dipole induced dipole? Doesn't that make the oil?
This is induced dipole. Oh, dipole induced dipole. I'm not going there. You'll never have to worry about it with the AP exam.
Okay. Because then, like, with that,
Yes,
oil
you
doesn't
could.
work. But
You could have a polar thing that runs into a non-polar thing, causing a temporary polarity to it, like kind of like happens up here. Not just because of motion, but because of polar.
oh, is it like iodine in water?
Yeah. Yes. Yes. Okay. Good with that one.
Mm-hmm.
Finally, what's our last type of intermolecular attraction? The hydrogen bond. Right, hydrogen bond. Don't be misled though, it's not actually a bond. It's still just an attraction, and so we just don't call them hydrogen attraction, we call it hydrogen bond. But it is just an attraction. Hydrogen bonding is just a very strong dipole attraction. It involves hydrogen being attached to FON or Cl. And I'll show you an example of what I mean up on the board.